Hi, so this is going to be a two-part lecture. Um, so this will be the first part of your atmosphere notes. You can find those online, Google Classroom, Wednesday, January 27th, Thursday, January 28th. All right, so we're going to talk about the atmosphere. We've kind of done several activities and some stations on it, and we're going to just kind of make sure we know what we need to know. The test will be next week, first week of February sometime. So you should be able to tell me what the composition of the Earth's atmosphere. Composition means what it's made of. What are the layers of the Earth's atmosphere? You should be able to tell me those in order. First, second, third. How does the sun's energy impact weather and the atmospheric movements? And what are the four major cloud types? So hopefully when you're done, you will be able to answer those. All right, so atmosphere. The atmosphere is a layer of gases that surrounds the Earth. So your first blank, you could say 5 layers of gases that surround the Earth. You could say atmosphere is you choose. I'm going to talk. You're going to fill in the blanks. Sometimes, or most of the time, all the words are going to be on the slide that goes onto your paper. Sometimes you'll just have to listen to me talk. So what's the purpose of the atmosphere? 3 purposes: to support life on Earth by protecting us from dangerous electromagnetic radiation. Remember, scientists like to use big fancy words. Electromagnetic radiation is one of those. It's spelled just like it sounds, electromagnetic. And these these type of radiations, that encompasses a whole bunch of them. And hopefully at the end of the year, we'll talk about them. The second purpose is to create and control weather and climate. Without our atmosphere, we wouldn't have climate that could sustain humans and animals and plants. The third purpose is to provide gases to the plants and animals they need to breathe. Remember, plants need carbon dioxide and they turn it into oxygen, and animals need oxygen and turn that into carbon dioxide. So hopefully you have that first section, atmosphere, all filled in. We're going to move to the next section. Composition. Composition just means what it's made of. So let's talk about what the atmosphere is made up of. 78% nitrogen, 21% oxygen, 0.9%, not even a whole percentage point, 0.03, 3/100ths carbon dioxide, 0.17 of trace gases. Trace means a very small amount. Abundant means a lot. Trace means a little. And those trace gases include neon, methane, krypton, and hydrogen. So real quick, do you remember the chemical symbol for neon? Capital N, small e. How about the chemical formula for krypton? Big K, small r. How about hydrogen? Big H. Methane is actually a combination of multiple elements, so it's called a compound, and I don't remember it off the top of my head. All right, so something that is interesting in this particular slide is the nitrogen. When we breathe, most of the gases is nitrogen, but our human body, our animal bodies, cannot use the nitrogen as a gas. The nitrogen has to go through the nitrogen cycle for us to use it. So I find it very interesting that the most abundant gas we can't use in that form. We can only use the 21% oxygen. All right, next section. We're going to talk about gases important to life on Earth. So nitrogen is a big N. Nitrogen is removed from the atmosphere by bacteria and lightning. So this is part of the nitrogen cycle we already talked about. We can't use nitrogen as a gas, so it has to go through the nitrogen cycle. Bacteria has to use it, and lightning has to go through its process to create some nitrogen. And nitrogen compounds are used by plants in their growth and development. So in order for plants to grow and develop, they have to have nitrogen. In order for human beings to work, we have to have nitrogen. But we can't use the gas nitrogen in the atmosphere. The nitrogen has to go through its nitrogen cycle. And one way we do get nitrogen is by eating fruits and vegetables. Part of the reason why you're told always to eat your fruits and vegetables. Oxygen, capital O. Oxygen actually in the atmosphere is found in pairs. So O2, pretty sure nitrogen is too. So oxygen is released into the atmosphere by plants as they photosynthesize. So remember, plants take in carbon dioxide, they breathe out oxygen. They're just the opposite of us. Okay? Water vapor, H2O. So H2O, we're going to talk about the gaseous form of water, which is called water vapor. And this amount actually varies in the atmosphere. If you think of Dayton, Ohio here, it's a wintertime, it's cold, it's very dry, so that means there's not a lot of water vapor. And you know this because of all the static and the static electricity you have. But in the summertime, it's very hot and humid, and we hardly ever have any static electricity. So our water vapor here in Dayton, Ohio, changes seasonably. And it also changes depending on where you're at. Like if we were to go to the equator right now, it would probably be very hot and humid most of the time. So we can't say like nitrogen is 78% most of the time. We can't say that for water vapor because it just varies. It changes too much. Water vapor cycles through the hydrologic cycle or the water cycle. Carbon dioxide, this is CO2. So if you take a minute, it's a capital C, capital O, little 2. So that means we've got 2 pieces of oxygen and 1 piece of carbon. But if you look up at water, we have 2 pieces of hydrogen and 1 piece of oxygen. So that 2 makes a big difference where you put it. All right, so carbon dioxide is removed from the atmosphere by green plants through the process of photosynthesis. So it breathes in carbon dioxide, puts out oxygen. Okay, so this is that section. You should have all the blanks filled in. Yep. Okay, next section. Complicated and confusing, and I'm going to try to make it as simple as I can. I like to actually bring out our old textbooks and show this to you, but I don't have those handy. So we're going to talk about pressure. Pressure is exerted on the Earth by the atmosphere. Okay? It decreases as I increase in altitude. So as I walk up a mountain, as I increase the altitude, the pressure gets lower. And that kind of makes sense. Think about when you're in an airplane. If we didn't have a pressurized cabin inside that airplane, there wouldn't be enough oxygen for us to breathe because there's not a pressure there. We'll talk a little bit more in a minute. There are 14.7 pounds per square inch at the sea level. We're above sea level, so ours would be less. Let's see, New Orleans is below sea level, so theirs would be more. Here's a great way to think about atmospheric pressure. A lot of us have either participated in a human pyramid or we've seen one. I've participated on the bottom row in high school and college. So my arms were really strong and my back was really strong because I was feeling the weight or the pressure of everybody above me. So that's kind of like us standing on Earth. We've got all of this air pressure. If we look straight up in the sky, we've got all of this air sitting on our shoulders and our head. We don't feel it because our bodies are made this way. We do notice a difference in the atmospheric pressure. I do. Some people are not as sensitive. I'd notice, like if I were to go to Denver, Colorado, they're called the Mile High City because they're a mile high. So there's less pressure. So I often get a headache and feel lightheaded because there's not as much oxygen up there. There's not as many particles pushing down on me. Another great example is a lot of us have gone to the swimming pool and gone to the deep end and gone to the bottom of the deep end. And you notice the pressure on your ears and your nose the farther down under the water you go. That's So think about in a swimming pool, at the bottom of the pool, you're standing on earth, and all of that water is air pushing on you. Our bodies are used to it because we do that every day, so we don't notice it as much. It's only when we change and we, I don't know, hike up, pick a mountain, hike up a mountain. Some of the mountains are so high, you've got to take extra oxygen with you because the pressure and the amount of oxygen is so little. There's not enough to breathe. So, pressure, atmospheric pressure. Um, so, when we talk about pressure, we also need to consider density. And we know from science class last year, I think in Mrs. Linzer's class, she usually gives you these little cubes. They're all the same size, but they're made out of something different. And you figure out the density. You put it on a triple beam balance and figure out its mass. And then you figure out the volume, usually length times width times height. And you divide those two and come up with density. And if I were to find, I don't know, the density of a plate, I would actually have to mass it and then calculate using a computer, a calculator and a math formula, figure out the volume. In everyday life, there is not one instrument that you can put it on and it automatically calculates the density. The lucky thing is, for the atmosphere, we do. It's hard to figure out the density of gas, but we do have an instrument. It's called a barometer. So when I fill this tube up with liquid and fill this cup up with the same liquid and turn the tube upside down in the liquid, the air pressure pushes down on this mercury. And when it pushes down, when the pressure is high, it pushes it up that tube, so it goes higher. When there's not a lot of air pressure, it doesn't press on this mercury, so this goes down. So a barometer is pretty cool to make. The greater the altitude, the higher I go up that mountain, the fewer particles there are, the less dense it is. And this picture is a great example. So if we look at this first box, see all those blue particles? There's a lot. So that means that's got a high density. But if I go up that mountain and I go to the very top box, there's not as many blue particles, so the density isn't as much. So that means it's harder to breathe up here at the top than it is the bottom. It means that I feel less pressure at the top than the bottom. Okay? So atmospheric density. So let's talk about atmospheric warming. We've kind of talked about it in the last test. We'll talk about it a little bit more, but atmospheric warming has to do with solar radiation. 49% is absorbed by the Earth's surface. 20% is reflected back to space by clouds. 20% is absorbed by the atmosphere in clouds. 6% is scattered by the atmosphere. And 5% is reflected by the Earth's surface. So as long as we keep these numbers kind of constant, everything works just right. Our atmosphere is doing what it needs to do. It's keeping the temperature of the Earth just right. It's not making it too hot, not making it too cold. What happens is when we add too many greenhouse gases, it changes the ability to absorb and reflect. It throws these out of whack, and it starts changing our climate. Okay? So let's flip to the next. We are not going to do this. We are not going to do this. So we're going to go to layers of the atmosphere. So you're going to have a test next week, and you are going to have to know the layers of the atmosphere. You'll need to know them in order. I may or may not give you a picture, and you have to label each of the layers. But you will need to know the layers. You will need to know what's in the layers, and you'll need to talk about the temperature of the layers, and we'll get there. So you need to know the troposphere, stratosphere, mesosphere, thermosphere, exosphere. I actually memorize them in reverse. I put the exosphere on top and then the thermosphere because I remember them that way. All right, so you need to know the layers in order. Let's talk about layer boundaries. So we've got layer boundaries. Um, they're the differences in temperature separate each layer from the one above it. So if we take a look, this light blue here is the troposphere, and the red lines kind of go into the left. And then we have the boundary, tropopause. Notice that it stays about 45, 50, stays about 55 the entire time through the troposphere, so it stays constant, the temperature. Then the stratosphere, it kind of looks like it's getting hotter. And then the stratopause stays about the same, it's the same temperature, -5. Then the mesosphere looks like it's getting colder. And then the mesopause stays the same. I'm going to say it's about 90. And then the thermosphere gets warmer. And I'm going to bet the exosphere gets colder. So the differences in temperature separate each layer from the one above it. And you're going to notice it's like a cycle. One gets cold, then hot, then cold, then hot. So I'm going to guess the exosphere gets cold. Temperature remains constant through the boundaries. So if you look at tropopause, it doesn't change. The temperature is a straight line up and down, and it's about 55. Stratopause, straight line, about -5. Mesosphere, straight line, about -85, 90. The boundaries are called pauses. So we've got the tropopause, the stratopause, the mesopause. Okay, not sure why they called them pauses. But we've got the troposphere, then the tropopause, stratosphere, then the stratopause, mesosphere, then the mesopause. Okay? So on the test, I'm probably going to give you this graph, and I'm going to ask you what happens to the temperature in the troposphere. So if it's going to go from 15 to -55, is that getting hotter or colder? Colder, right? It's going to go from -55 to -5. It's getting warmer. It's going from -5 to negative, I don't know, 90. It's getting really cold, right? So you need to be able to tell me which ones are staying constant, staying the same temperature, which ones are getting hotter, and which ones are getting colder. All right. So we're going to talk about the tropopause. The tropopause is the lowest layer. It's the one we live in. It's where the plants and the animals are. It's where most of the weather is. Most of the airplanes are there. Most of the atmospheric air is found here. It extends from 0 to 14 kilometers. I think we did the math, and for those of us who've taken airplanes before, like if we're going to fly at 15,000 feet, that's well below the top of this. The troposphere goes to 46,000 feet. So the commercial airlines that we fly in as human beings are usually in the troposphere. The ones that go in the stratosphere are the jets, the ones that the Air Force and the military, those guys fly. Air temperature decreases with the troposphere. So it's getting colder the higher up you go. The more I walk up that mountain, the colder I'm getting. So troposphere, you're going to need to know lowest layer. You're going to need to know its temperature and what's happening with its temperature. You need to know it's the first one. Label it. Virtually all the weather occurs here. Okay? So let's talk about weather in the troposphere. Winds. A lot of us missed this question on the test. Winds are caused by the unequal heating of the Earth's surface. And this unequal heating causes differences in pressure. So like if you were to watch the Weather Channel or a weather forecast, you're going to see the letter H and the letter L on the map. And there's going to be storm fronts around those. So those are pressures, and those pressures happen because of different temperatures. Okay? Because we know hot air rises and cold air sinks. So that's going to cause some movement of the air. Moisture is water vapor. We've talked about water vapor. It moves through the water cycle. Humidity, This depends on the amount of water vapor in the air and the temperature. Um, Dew point is the temperature at which water begins to accumulate on surfaces and condense. So we've talked about this. And water vapor condenses to form clouds. So we know here in Ohio, on a day like today when it's cold and cloudy, there's not a lot of humidity. And I know that because um, I get static and I get shocked a lot. And when I get static and I get shocked a lot, there's not a lot of humidity or moisture in the air. But in the summertime, when it's hot and sunny, there is a lot of moisture. It's hot and sunny. There's lots of evaporation happening. There's lots of moisture in the air. So there's not a lot of static in there. All right, so let's talk about clouds. So we've got four main types of clouds: the cirrus, high wispy, I remember ice crystals. We've got the cumulus. We've got the stratus, I think that's what today is. And we've got the nimbus. During the station organizer, there were 8. If I have you remember any, it's going to be these 4. All right, 2 more sections for today. We are not going to do this part. So let's talk stratosphere. The air temperature increases. That means it gets hotter the higher you go up into it. So if I'm climbing that mountain, it's actually going to get hot in the stratosphere instead of cold. And that's because of the ozone layer. It absorbs sunlight, and ozone is O3. So in the stratosphere, we have the ozone layer. Really important. This is 14 kilometers to 50 kilometers. It is very calm here. There are less air particles. The density is less. The pressure is less. So if there's less air particles for this jet to fly through, that means there's less friction. That means there's less heat. That means it's more, that it uses less fuel. So it's very calm here. The ozone is found near the bottom of this layer. Ozone is super important. We're going to talk about the ozone and stop then. All right, the ozone. The ozone is a gas, and this gas is O3. Oxygen is O2. If we add another oxygen, it's ozone, O3. Ozone is considered a pollutant when it's not in the layer. So if we have ozone down here where we are in the troposphere, it's considered pollution. Ozone we don't want to breathe, but O2, oxygen, we do. The ozone layer absorbs solar radiation, so it helps block out the UVA and UVB rays that would cause skin cancer. It releases heat. That's why this sphere is so hot. It protects us from UV rays, ultraviolet rays. So if we didn't have the ozone layer, we would have lots of UV rays, lots of skin cancer, or our skin would be totally fried. So this is where we stopped on Wednesday, the 27th, and I will try to make another video to finish the rest of the notes for Thursday.